Welcome back for session number 2 this week, 2 of 3. So I think I was a bit quick in writing down the spectral theorem last time, and so I'll do this again at a more leisurely pace and explain a few more things about it. Okay, so first of all, one thing I think I didn't say clearly enough would be that so we have abstract Hilbert spaces. So this would be an axiomatic description of the structures, like the scalar product, the norm and stuff, and some properties it has to satisfy, and concrete Hilbert spaces. So these are basically the spaces L2 of X with some measure. And so one thing I failed to say somehow is how are they the same? Right, so every concrete Hilbert space is an abstract Hilbert space, and the scalar product of so L2 of X mu is the set of functions from X to C. They are supposed to be measurable. And most importantly, the integral over X of X squared is finite. Right? So this is what the 2 in L2 refers to, square integral. And then for two such functions, the scalar product in this space is just defined as the integral like that. So this definition of the scalar product will satisfy all the properties of an abstract Hilbert space, provided, with one subtlety here, modulo norm phi 0 elements. So there are functions whose integral that are non-zero, whose integral is 0. For example, a function that is 0 everywhere except at a single point, and the measure is ordinary Lebesgue measure on the line, let's say. Right? So that sort of function has 0 integral, because the point has 1 to 0. But still it's not a 0 function. So really, this is, if I just write the space of functions like that, it would actually not be a Hilbert space, because it fails to satisfy one of the axioms, namely that if the scalar product of the function with itself, that is the norm square, is 0, the function should be 0, or the element should be 0. So actually, in all these spaces, we have to identify elements that differ only by a measure 0. So these functions are not literally, the elements of L2 are not literally functions, but classes of functions modulo almost everywhere. Equivalent almost everywhere is the standard term in measure theory for saying that something is true except on a set of measure 0. So functions that are 0 except on a set of measure 0 are 0 almost everywhere, and they just count as a 0 element of the Hilbert space. Right? So this looks very convenient. You have functions, but well, if you're quite precise, you don't have functions but classes of functions up to this kind of equality. And that is sort of a necessary consequence for making this thing satisfy the axioms of a Hilbert space. Okay, so now, so how are they the same? So the isomorphisms of Hilbert spaces are called unitary operators. So there would be a unitary operator from L2 they're the same because there would exist a unitary operator. And the unitary operator is just the kind of isomorphism that Hilbert spaces are asking for. So all the structures of an abstract Hilbert space are just mapped into each other. So each vector becomes another vector. Sum becomes the sum. Multiplication by a scalar becomes a scalar. The scalar product becomes the same scalar corresponding scalar product on the other side, and so on. Right? So this is just a renaming or identifying or mapping every function here to something in whatever abstract space, or conversely, right? And so in such a way that the structure of these two spaces is completely, the abstract Hilbert space structure is completely transferred. So from the point of view of abstract Hilbert spaces, a unitary operator is just a renaming of every element, preserving everything that is relevant about these elements. Okay, so another thing that came up in the spectral theorem was a multiplication operator. So this is the same as a diagonal operator in a concrete Hilbert space. So in order to say what a multiplication operator is, you need this. You cannot say this in an abstract Hilbert space because you don't have, the language isn't rich enough for that. But if you're in such an L2 space, you can say that. And here's the definition. So in order to define what the operator does, I have to apply it to a general element, let's say psi, right? And here's how it acts. The value of the function at some point will be just multiplied by some function that depends on x. So this is what is called a multiplication. Now again, there is the same sort of almost everywhere identification. If two different functions are the same almost everywhere, then this will also be the same almost everywhere, and so on. So all this matches up. But this is the basic idea. Why is that? Why do I call this diagonal? So in L2 of x, so this is the space for the counting measure, where the scalar product is just the sum. I would say that a psi, well, at x, well, I can write the same equation, but what does it mean? Well, okay, so let me put it differently. In L2 of x, there is a standard basis. Right? So I will usually just write that as a cat. And this is a function. So ex of y is delta x1. So that's the function that is 1 at x and 0 otherwise. Now if I consider the matrix elements of such a multiplication operator, so this is the scalar product. Let me just write it out again. Ex A mapped on EY. So let's put in the definition of the scalar product. which is the sum over, now I need another dummy index. So this is Ex of Z, complex conjugate. It doesn't matter here because it's a real thing, but just to make sure that we follow the rules. So then it's A, E, Y at the point Z. Okay? I'm just putting in definitions now. That's the sort of exercise that we do. To go through things like that and really look step by step what you have to insert. Now, this is the sum over Z. This is the delta XZ. That makes the sum easy. And now here, this is a multiplication operator. So this is some function. And if I operate with A, with the multiplication operator on that, I would have A of Z, value at the argument, and an EY of Z, which is a delta Z Y, YZ. Okay? Now if I do the sum, the only way this can be non-zero if X is equal to Y is equal to Z. That's the only non-zero term that is possible here. So this whole thing is delta XY times AX. So a multiplication operator in this discrete setting is exactly an operator whose matrix elements in the canonical basis are diagonal. So it's a diagonal matrix. Right? But we generalize that to this wider setting of concrete spaces, L2 spaces. And so what the spectral theorem does now, it characterizes the following situation. So you have operators A1 to K, I think I call them, they would be B of H. And I would call them jointly diagonalizable, or jointly diagonalizable. So this is I want to define this term. If there's one unitary operator, that doesn't depend on which operator I take, right? So if there is a unitary operator from, let's say L2 of X, some concrete Hilbert space to H, such that now I have to write operators. I have to turn every operator of these A's into an operator of the complete Hilbert space. So this looks like that. Right. So this operator starts in L2, maps to H, where I can apply this operator, and U star maps back to L2. So this is an operator in L2. Right? So each is a multiplication operator. Okay, so the question is when are such operators jointly diagonalizable? If they are jointly diagonalizable, I can basically turn my whatever Hilbert space I had. I can use this unitary isomorphism with an L2 space, and instead of operators, I have to work with functions. Right? So this is much easier, and I'll show several applications of that. Right? So this would make these operators particularly simple at the same time. Right? Now, when is this possible? Now, one thing that is clear from this definition is that multiplication. So let me just the spectral theorem says gives the conclusion, and I've written that already last time, but let me just do this more explicitly now. The spectral theorem says this is the case if and only if now, yeah, so the AJ or A1 to AK and A1 star to AK star all commute. That is, any two of them commute. Commute just means that AB is BA, right? So it's a combination of the multiplication. Now, let's prove it, and let's prove the utterly trivial direction of this to see why this is a good condition. So proof of the trivial condition, proof of the trivial direction. So suppose you have two operators that are jointly diagonalized, then so such multiplication operators always commute. Is that clear? If you have AB, right, and then the one multiplies with a scalar function A at x, and the other multiplies with a scalar function B at x. And because you're just multiplying with numbers for every x, this is commutative. Right? So U star, no, let's say AI, AJ, this any such product. What does it look like? I can write this as U star. Oh, did I say what unitary operator is? Well, it's one that maps all the structure. I did say that. But there is a simple equation that expresses this, which is to say that U star equals to U star U equals to the identity. No, that's wrong. This is the identity on H, and U star U is the identity on L2. So you couldn't really say that U star U is equal to U star. These are operators that live in totally different spaces. They cannot be equal. So, but of course, the notation. If you forget which identity it is, it's suggestive to write it like that. But please don't. Okay, so the AI can be written as U star. AI, U star, AJ, U star. I was just throwing in a couple of unitaries. Now these two commute because they are multiplication operators. And if I do that backwards, this is equal to U, and now the whole thing with I and J interchanged. And then if I again use this identity, I have AJ, AI. Right? So unitary, and this is a computation that after a little bit of experience with the quantum stuff, you don't have to do anymore, because you know that unitaries map all the structure from one space to the other, so if they commute in one space, they commute in the other space. And this is just expressing this automatic isomorphism that unitaries always give you. Now, the only thing that remains to compute for the trivial direction is I'm also claiming that the adjoints here commute with each other. And for that, I only need to show that the adjoint is a multiplication operator. The adjoint of a multiplication operator is a multiplication operator, because then obviously they're all multiplication operators simultaneously. transformed with the same U. Of course, this is essential. Right? Each one separately might be diagonalizable, but not jointly. So, so the only thing that remains is to compute the adjoint of a multiplication operator. So let's do that. So if A is a multiplication by A, by this function, and then I want to compute A star. Right? So this is a pattern. This is something that this proof can only start in a certain way. It's obvious how it has to go. It's a sort of boring thing that just has to be done. Right? So in order to characterize these operators, I have to go back to the definition of the adjoint, which is in terms of all scalar products of this operator. Right? So I have to compute all the scalar products of this operator. And then by definition, this is A phi psi. Now this is the integral of A phi of x. So this is another wave function times psi of x. Now this is equal to the integral mu dx of a product of three factors, namely phi of x star, A of x star, psi of x. Right? Now I've written it in this suggested way that it doesn't matter which order I multiply this stuff. So the way this comes out is, first it really multiplies the phi, but you can think of this as multiplying psi. So it's just a multiplication operator with a complex conjugate function. So this is equal to, call this, this then has to be A psi star. And so this is again a multiplication. Okay, so this is why operators that can be diagonalized have to commute with their adjoints, because both of them would be multiplication operators, and therefore they have to commute. Right? So if A star is equal to A star A, you say that A is normal. That's a definition. And there are two important special cases, e.g. A is unitary, because then A star and A star A are one, so that is in one space. Right? Here I was defining unitaries between different spaces, and there, of course, you have this U star U is not equal to U star. But of course, if that is the same space, it makes sense, right? But our standing assumption here is that A is an operator on A, so it is already in a single space. It doesn't make sense to diagonalize an operator between different spaces. Well, not directly. It's called the singular value decomposition. So, and of course, the other condition where this is true, so for unitary and when A is equal to A star, then we say that this is Hermitian. Right? A is Hermitian or self-adjoint. Now, these two come with a condition on the spectrum. I haven't defined the spectrum. So the spectrum, spec of A1 to AK. So I have this situation of some normal operators that commute with each other. So what is the spectrum? The spectrum is the set of values by which I multiply. So this is a subset of C to the K. So each of these is a complex number in general. So of course there could be in particular they could be real or a unit circle or something like that. So they could be in a special subset of C, but generally speaking there would be subsets of the complex plane. And so you can look at these tuples. Now here again there is a measure zero side because if I change the function I multiply with at just some point or on a set of measure zero, this will not change the operator because this will give the same vectors, because vectors that differ only on sets of measure zero are by definition the same. Right? So I here have to say up to sets of measure zero. So the form of the exact definition of the spectrum would go like this. I look at a point in CK, and I look at a small ball around that. No, I look at a small ball around that point, and then I look at the values of x for which this tuple lies in that ball. And if the measure of that set is non-zero for every radius of the ball, for every non-zero radius of the ball, then I call that an element of the spectrum. So this is what is really meant by this up to sets of measure zero. So outliers that happen only on a set of measure zero in X are irrelevant for any operator, therefore also for this definition. And if you define that properly, automatically the spectrum will be a closed set, because you define it in terms of small balls. Okay, so, and now of course this also goes for a single operator, right? That is normal. So in this case we have that the spectrum of A is contained in the real line, and this, in this case the spectrum is contained in the unit circle. Which is very easy to check, right? Because the adjoint is multiplication with the complex conjugate function. And the function is almost everywhere zero, almost everywhere equal to its complex conjugate, if it is almost everywhere real. Right? And that is, so this almost everywhere takes care of this part, but loosely speaking, a function that is equal to its complex conjugate is real. That's what I'm saying. And a function that you can just drop out of the, so if you apply that in both parts of the, in both factors of a scalar product, it is supposed to not change the scalar product. So a of x absolute square has to be 1, almost everywhere. And that is the solution. So the spectrum would be its unit circle. Okay. So a few general remarks. So one is the functional calculus. So you must have encountered various occasions where your quantum mechanics professor was taking a function of an operator. For example, e to the I h t, something like that. Right? So there's the exponential function, and you take the exponential function of an operator. So how do you do that? Right? So here, I'm looking at a function which goes from the spectrum to C. So this is a scalar function. This is a numerical function, of course, from tuples of these values. I'm generalizing this now to k operators, right? So, so I have some function like that. And then so then I can apply that function to the operators. Right? So instead of scalar values, I can now just plug in operators instead. And I do that in the following way. So this is the well, I take the same unitary that would turn this into the multiplication operator. That's U star in before and after. So this is going to be a multiplication operator, right? And this will multiply. Well, let me just write what it does. Right? This is a multiplication operator, and this multiplies with f of a1 of x, a k of x, which is well defined because that's what the function does. So all this functional calculus completely works on the level of multiplication operators. This is why multiplication operators are so convenient, because you can just apply a function to the tuples of values that these operators take. So in some sense, the spectrum are like the values that an operator takes. And this is a general definition of the functional calculus. Now there are different versions of this functional calculus, depending on what I know about this function. So, for example, if this function is analytic, that is, it can be expanded everywhere in the power series, then I can write this in terms of the power series. Now let me start with the simplest one. If this function is a polynomial in k variable, complex variables, then you can check immediately that this will be the corresponding operator polynomial evaluated on non-commuting arguments. Well, they are actually commuting arguments. That's why it is. So if you have a polynomial like of two variables, x and y, let's say, for example, x times y. This is well defined for operators. If you say what the ordering of the factors is supposed to be, right? Then of course you can apply it also to operators that don't commute. You have to, if you want to apply a polynomial or compute a polynomial of operators that don't commute, you have to specify the ordering. And then this kind of information wouldn't be enough, because you need some ordering information on top of that. Actually, quite a lot of information. Right? Because then if AB is different from BA, these are just linearly independent monomials, and they have to be treated like totally different things. But here in the scalar function, they would be treated like the same. So this is why the function calculus implicitly demands that the operators that you look at commute. Then it doesn't matter how you evaluate it, you know. So the simplest installment of this function calculus is just doing it for polynomials, and then it is nothing but taking polynomials in the ordinary sense. So the next level is to turn the polynomials into polynomials of infinite degrees, also known as power series. So this is called the analytic function of calculus. And then this function has to be analytic. Now, the next version is continuous function of calculus, but this has to be a continuous function, and then you know that this function f of the operators will be in the norm-closed algebra that is generated by these things. So this is the C star algebraic function of calculus. And then if you know that this function is just measurable, so for example, it could be a step function or something like that, then you are in the world of for Neumann functional calculus or weak star functional calculus. So depending on what your analytic conditions are, there are different installments of this functional calculus, and they come with different information that you can get from these operators. For example, how you can compute that. Can you approximate? In what sense can you approximate it by a polynomial? Okay, so this is the functional calculus. So this joint functional calculus of several operators. Why am I doing that? Well, on the one hand, it's because it's natural, but also because you've already seen that in your quantum mechanics course. And what people so jointly diagonalize. So in quantum mechanics 1. Or should I write 101? In an American university, it would be 101. So in quantum mechanics 1, you take the hydrogen Hamiltonian, you take L squared and L3. Right? So you jointly diagonalize the Hamiltonian, and because it's rotation symmetric, it commutes with the angular momentum. Actually, it commutes with all the angular momentum components. But they don't commute with each other, so you don't get a good way of you cannot apply the diagonalization theorem, right? So you have to pick a subset of angular momentum operators that commute with each other, and the typical choice is L squared and L3, and one of the components. So and the whole point of this exercise of doing that is that you get a simple form of the Hilbert space. You can write it in terms of joint eigenfunctions of these, which is just the same as saying that you jointly diagonalize these operators, at least on a certain subspace, like a subspace based thumb space. Another example of this is a band structure. So H of would be the kinetic energy, whatever the mass is, right, plus the periodic. So your potential is periodic in R3, right, because you're looking at a lattice system, and then there are certain multiplications with which this Hamiltonian commutes, namely those certain translations that are a symmetry of this system, namely when you shift by an entire lattice space. Right? Now, the joint spectrum of this commutes with lattice translations. Now, the joint spectrum of the lattice translations are unitary operators, so their spectrum will be on the unit circle. Now, if you have three directions of lattice translations, you get three torus, basically. And the typical way to write this three torus is to cut it up and flatten it out so that you take it as the elementary cell of a dual lattice. And this is called the Riemann zone. Right? So basically, the joint spectrum of the translations is called the Riemann zone. And over that, together with that, now you diagonalize your Hamiltonian, and you get a subset of Riemann zone cross energy. And this is called the band structure of this. And probably in solid state physics they don't explain it exactly like that. But that's basically what it is. And so these are actually familiar examples. So the slogan here would be finding a maximal set of commuting observables. And Okay. So what is it I want to say? So they let us write out the discrete finite case of the spectral theorem. Discrete finite case and A star is equal to A, so the Hermitian case. So I have some Hermitian operator, and then what does the spectral theorem give you? It gives you a decomposition of this operator with AI, PI. Well, this is finite because, for example, this will be finite automatically when we're in a finite dimensional Hilbert space. And then these are the eigenvalues. And this is the projection to the eigenspace. Right, so this is just the eigenspace. And then as a subspace of the Hilbert space, subspace 2, so this is called the eigenspace, and the orthogonal projection onto that space is what you put here. So this arises in the functional calculus by taking a characteristic function that is 1 at the eigenvalue and 0 away from the eigenvalue. So the possible multiplication values here, if you think of a finite dimensional space, then x is actually takes finitely many values only. So also the A of x's can only be finitely many. So there have to be has to be a lot of room in the spectrum, right, between the spectrum. So they're just the discrete points, the eigenvalues, and that's what that gives. And so these PI are an orthogonal composition of the identity, right? So they satisfy PI star Pj is delta Ij Pi. So they're orthogonal projections. If you put I equal to j here, it says that P star P is P for each of them, which means that each of them is Hermitian. P star P is always Hermitian. So they're automatically Hermitian, and this also says that they're orthogonal, and also the sum of the PI is the identity. So this is an observable. And so what I define an observable as given by a set of positive operators that describe the probability for a certain response. Now, here I have exactly that structure, positive operators that add up to 1. And this kind of observable is basically the only observable that you find in most textbooks. And you immediately recognize it in the phrase that if you measure an observable A, people usually then call A the observable. Right? If you measure an observable A, the possible outcomes are the eigenvalues. Right? So, and the probability for getting this outcome is the expectation of the corresponding spectral projection. Right? So this is the way the Born rule, or generalized Born rule, is usually stated in these courses. So we will have many situations where the PI actually should not be projections, but are in a natural way are other positive operators. Right? So generalizing that is a very useful thing for quantum information theory, and we'll just do that throughout, but just to make the contact with what you most likely heard in your quantum mechanics course if it wasn't me. Okay, so this is POVMs and PVMs. So maybe look at some further examples. So I'll erase first. Okay, so maybe let's go back to the simplest case of it all. Qubits. So whenever I should by definition, qubit is a quantum system with that Hilbert space. So, who of you has not seen the Bloch sphere in quantum mechanics? Who has seen it? Okay. So anyway, so I mentioned that states are given by density operators. That is, rho is positive and trace rho is 1. And then if you make a coordinate system and you look at the expectations of the Pauli matrices, rho sigma 2, base rho sigma 3, so sigma I Pauli matrices. Then, if you look at what you can get here, then you do get, well, some kind of all. Anybody recognize all here? I should have practiced a little bit. This is horrible. Okay. Not that I haven't done this before. Okay, so how do I get this? Well, first of all, these operators, the Pauli matrices, square to 1, so their expectations have to be between plus and minus 1. So this will sit in a cube. And if you look at the expansion of the matrix in terms of the Pauli matrices, you see that these the expansion coefficients, or the fact that the determinant has to be positive, difference. Now I'm mentioning that because if I have some density operator that sits somewhere in this sphere. So this is an operator. So what is its spectral decomposition? If I do that decomposition that I just erased. So what are its eigenprojections? Can you say where they are? Any guess? Yeah, on the top. On the top? Yeah, well, this is kind of generically in the ball somewhere. Right? So actually, I can write rho as, let's say, r plus p plus r minus p minus. Right? And r plus r minus have to, or whatever, right? Plus minus are just states. Right? So well, these are the eigenprojections. Now they are proper subprojections typically, right? Almost always. So in 2 dimensions, the only projections that are not 2 or 0 dimensional are the 1-dimensional projections. So these have to be 1-dimensional projections. So if I just take r plus equal to 1 and r minus equal to 0, that is, if I just take a 1-dimensional projection, I have a legitimate quantum state. We'll discuss that in more detail later. Those are the ones that have determinant 0. The 1-dimensional projection is eigenvalues 1, 0. So their product is 0. So they have vanishing determinant, which means that they're on the surface of the Bloch sphere. They're on the Bloch sphere rather than the Bloch ball. Right? So these things will be on the outside. Now R plus, if you compute the trace of the whole thing, the trace of a 1-dimensional projection is 1. The trace of any projection is the dimension of the space it projects to. So, so the sum of R plus and R minus has to be 1. In other words, this is a convex combination. So it has to be, a row has to be on the line joining P plus and P minus in the Bloch sphere. So actually, I have to find, and let me do this by hand, but my drawing is too bad for this, right? So here's the Bloch sphere. So I will have 2 points on the surface of the Bloch sphere, and rho will be on the line in between. Would this determine the spectral resolution? I mean, P plus and P minus? Well, no, because there are many lines I can draw through each point inside the ball. Right? Infinite. Uncountable. So one of them is right. Only one of them is the spectral projection. The spectral decomposition. So how do I get that? Well, there's one more condition, right? I'm not just saying that P plus and P minus are projections. They're also orthogonal projections. And so this is an orthogonal decomposition. And so where do I find orthogonal projections on the Bloch sphere? How do I describe that geometrically? Again? Yeah, so they're antipodes. So the line connecting them will go directly through the center. That's what's interesting. So now I have a point in the Bloch ball, and I want to write this as a convex combination of 2 surface points in such a way that the connecting line between the endpoints of this decomposition goes through the center. Well, therefore I have to take the line from the state through the center, extend that to the, so that it pierces the sphere, and those will be the spectral projections. Okay? So you couldn't just be like north-south, because that wouldn't depend on rho and of course the line projections do. Now, what kind of observables do we get on the Bloch sphere? Let's say I'll take numerical observables that have outcomes that are complex terms, and I take PVMs, I take projection value observables. So how would I get those? So again, we will have the spectral resolution of any observable will correspond to first picking 2 antipodal points. So picking any such projection value observable amounts to doing that, and assigning values to them. That's the least important one. But I take 2 antipodal points, and those would correspond to would give you the probabilities for the outcomes. So if I have such a projection, what is the probability for that occurring? So again, I have rho will be some generic point in the Bloch ball, and I have this decomposition into 2 antipodes that comes from the observable. So what is the probability for getting each of the results? How can you see this in the Bloch sphere? Well, first of all, this expectation has to be a linear function. The expectation as a function of rho will be an affine function, and so it respects convex combinations. So that is, the lines of equal expectation value will be planes, and there will be the planes that touch these 2 antipodal points, and they will be sort of orthogonal to the axis joining. So these will be the lines of equal value, and of course they're also equally spaced. So that's the way to look at it, and you have to see where you are, where the rho sits, on which of these levels it sits. So you could say, you project the rho to the axis, and then you can read off what the probabilities are. Right? So it will be some cosine of an angle if you want to. I think it's better to think about it geometrically. So this is the case when you have a projection value measure. Now you could also have observables that are not like that. So you don't just pick two antipodes. So the positive operators that add up to 1 here could be multiples of other projections. Now if the sum has to be 1, which means that if you look at the one-dimensional projections that correspond to the outcomes, I should have it right. So PDN corresponds to a pair of antipodal points. Or maybe antipodal, I don't know. There is a set of islands off Australia or New Zealand called the Antipodes. I think that's how they pronounce it. I think this is one of the most weird expressions of Eurocentrism that you can imagine. So you call something on Earth by, you identify it by its being just opposite to what you know. So the antipodes, anyway, so this is the PBMs. POVMs, for example, Fi could be some factor lambda I times Pi, and these are 1D projections. Now the fact that sum Fi is 1 just means that the sum of lambda I, Pi is the identity. So the PIs will be points, oh wait a minute. The trace of the whole thing is 2, right? The trace of the identity is 2. So maybe I should write this as 1/2. I'll do that here. No, that's 2. What do I want? 2. 2. So then by just taking the trace of this equation, I find, so the lambda I have to be positive, so that this operator is positive, and the sum of the lambda I now in this normalization has to be 1. In other words, I have a convex combination. And so sum lambda I Pi, the convex combination, these Pi are points on the Bloch sphere. Actually, the Bloch sphere is a 3-dimensional object, which means it only shows part of the picture, because the space of 2x2 matrices is 4-dimensional, or Hermitian 4x4 matrices is 4-dimensional. So this is actually the trace equal 1 plane of the 2x2 matrices. So this is why I have to juggle with these factors, so that I can show you something that is actually has trace 1. Now, so the PI would have trace 1, and their convex combination will be 1/2 of the identity. So of course these are states, they are density operators, so the convex combination is also a density operator, and it will be the chaotic density operator. That's what the condition requires. So actually I must have a collection of points on the sphere, and the only condition for these points is that their convex hull contains the center. So Pi are on the Bloch sphere, those on the outside surface, and convex hull contains the center. So that's the condition for a general POVM observable. Not completely general. I'm saying that this is a multiple of a one-dimensional projection, and so this is kind of special. But those are the ones that measure as sharply as possible, and we'll come back to that. Okay, so. this was Hilbert space notation and useful stuff. So so this is a very useful operation. It's absolutely not just useful; it's just indispensable. Which is putting together two subsystems. For example, I don't want to draw a house at all. This is a house. I think Bob should be simpler. No, I don't want to do Alice and Bob. They have to be called Alice and Bob. So this is called the separated labs scenario, and it happens a lot in quantum equations. Many things refer to that. And the idea is that we have a joint quantum system that is composed of two parts, and these two parts are actually sitting in different labs. So one is in Alice's lab, maybe some atom in a trap, and one is in Bob's part, maybe a photon between two mirrors. Well, it doesn't last very long. Anyway. So, and then just putting the two systems together is one way to do that, which is just each of them prepares such a system, and then they have a joint system, and they just declare it to be a joint system. But of course, it also could have been produced in a different way. So Charlie made it and sent them the parts. And that is usually much more interesting, because you can get entangled. But how do we describe this in quantum mechanics? So there is a standard rule for that in quantum mechanics. So Alice's system is a type of system that is described in Hilbert space HA, and Bob's is in HB. And then the question is, what is the Hilbert space for the joint system? So rule joint system is described in HA tensor HB. So this is the appearance of the tensor product of Hilbert spaces. Who has seen that in the quantum mechanics course? I think we should be pretty safe with that. Anyway, I'll give a brief explanation. Right? So this is equal to the Hilbert space that contains vectors that are of the form phi tensor psi, where phi is in HA, psi is in HB. With scalar product. So I can only define the Hilbert space if I tell you what the scalar product is. The scalar product is phi tensor psi. Maybe let's see how many Greek letters we know. What is a good eta? So this is supposed to be chi and eta. This is now I probably get confused. So the first scalar product is in A, the second scalar product is in B, right? So I just multiply the scalar products. The Hilbert space that contains such vectors, the scalar product, and the span term. write that is spanned by vectors of that form. Right? Now, this use of a definite article is very mathematical, and it means the following. So suppose I have any Hilbert space that meets this description. It's spanned by a collection of vectors that have whatever these names, right? And that satisfies this relation for the scalar product. So I have two different realizations of this. And the claim is there will be a unitary operator that maps one into the other in such a way that these product vectors are also mapped to each other. So, in other words, there is essentially only one way of doing that, up to the obvious isomorphism that is immer there. Always there, which is unitary isomorphism, right? So up to unitary isomorphism, there is only one space with this property, and that is the Hilbert space. Now, but there is a better way another way to define that, namely to realize that if I take the tensor product of complete Hilbert spaces, so there will be just L2 spaces with some measure. Then this is actually equal to the L2 space on the Cartesian product with the product measure. So the case that you all know of this example, two particles. So I have an L2 of R3, which is the Hilbert space for a spinless particle, R3 being the position space. And I have a tensor product with another copy of that, an electron and a proton maybe. Let's say all this Y. So this is then L2 of R6. dx dy. So in other words, rather than having wave functions that have only the coordinate of the electron and the other, you instead have wave functions that have two coordinates, depend on two coordinates, that is space coordinates, position vectors, one for the electron and one for the proton. That's exactly what you just write down for doing a composite system. Two particles in every quantum space. Right? So in that form, you must have seen it, and in this interpretation, the phi tensor psi is the following function. It depends on two variables now, and it's just phi of x times psi of y. Right? So taking the product function as you use it in a separation ansatz, is exactly this kind of tensor product element. So this is just an abstract way. This is the abstract Hilbert way, Hilbert space way. This is a concrete Hilbert space way. Now, why not just do it like this? Because this is certainly kind of natural. Well, there are different ways to represent the space that you're interested in as an L2 space, and you would like to have a definition by which you're not forced to prove every time that it doesn't depend on the way you've written your space as an L2 space. And this is what this definition does, without any effort, because it doesn't depend on that. So whatever you like. Now, so if phi mu HA and psi are, let's say, psi alpha, some collection of vectors in U bases, then the vectors phi mu tensor psi alpha are this collection. Is a basis for HA. A tensor HB, in which you can see the concrete version of this definition. But it's also clear that because you, yes, so this condition will imply that this expression phi tensor psi is linear in each factor. This is bilinear, which is actually a necessary justification for using the tensor symbol. So the tensor symbol comes from multilinear algebra, and automatically it combines two linear, it makes a bilinear function. So the universal bilinear function. That's called the universal property of a tensor product, and that also matches here. So anyway, so this is the basis, and then our Kepler notation. So in this expression, when you have to expand things in a basis, in a product space, in a Hilbert space product space, then the only symbols in this expression that actually carry relevant information are the indices. The phi just is the name of the basis, and that is typically clear from the context. This psi is the name of the other basis, typically clear from the context, and the tensor product just means that you combine the two vectors in the only way you know how to combine them. So you just write it like that. So you just put the labels next to each other. This is an extension of this notation where you don't write the basis vector, but only the label into the Kepler product. Okay, what else do we have to do? We have to check. You have to check that this description is reasonable. And in particular, I mentioned that one way for Alice and Bob to have a combined system of one of type A and one of type B, one subsystem of type A and a subsystem of type B, is to just make them independently. So each such process would be described by a density operator, and we have to see how to describe this way of making path. So how do I? So actually, in my pictures here, this would be the cartoon of Alice producing a state called rho A, and keeping that in her storage. And Bob does a similar thing called rho B. I sometimes leave a gap here. Too lazy. So now they want to combine the two. And so they now they have a preparation, and I claim that this should be the tensor product of corresponding operators, which I'm going to define in a minute. Now this is one thing they can do. The other thing they can do is making measurements completely separately. And for example, Alice could measure A. Maybe I should just call that B here. And this has a yes-no outcome. Does anybody know how to draw an AND gate in logical circuitry? Something like this. So this is an AND gate. And the box has this outcome. So they make a yes-no measurement, and the joint measurement has outcome yes if they are both saying yes. So we really know what the probability for this is without defining a tensor product, because they are just two separate experiments. They're just all the quantum part is done separately, and only the post-processing is done by combining these with an AND. Right? So I have events from Alice, ones and zeros, events from Bob, ones and zeros, and I want to, and they have some known probability, the ones, And then I ask for the probability for both being 1. Now these are independent experiments, so we should have something like trace row A tensor row B. Let's call this FA. What should this be? Well, that should be the product of these probabilities because they're independent. So this trace, of course, is in HA, and this other trace is in trace row. Now, then the question is, how do I have to define these tensor products of operators so that this makes sense? So tensor product of operators. I want to define this operator. I know this is supposed to be A tensor B. B, straight B. Is supposed to be a bounded operator on HA tensor HB. Right? So now I know. So this is an operator on a certain Hilbert space. And I know some typical vectors in that space, namely the product vectors. So I can apply this guy to phi tensor psi, because I know these are for sure in that Hilbert space. So what does this operator do with this vector? It has to be another vector in the same space. And the only thing I can write with the material that is on the board is clearly A phi tensor B psi. And it wouldn't make any sense to apply A to psi because they live in different spaces. So this is the only thing I can actually write down in this subdivision. Now this is not a full definition in some sense because not all the vectors in the tensor product space are of this form. The tensor product is generated by these, meaning that I need linear combinations and normal limits if it's infinite dimensional to get the full space. But this is supposed to be a linear operator. So the linear combinations can be pulled through, and this is after all this essential bit of information that I need. The other bit that I need is I have to prove that this sort of operator is actually bounded on the tensor product space, that A and B are bounded, but that luckily is the case. So plus linear and continuous extension. So this is the essential core of the definition, but it's not the full definition. You have to say, in addition, that this is supposed to be a bounded linear operator. And therefore you know how to compute it on arbitrary values. Okay, so this is one thing that we need, and then of course we see that row A tensor row B times FA tensor FB. Well, apply that to the product vector. What does it do? It just neatly first applies F to the first vector and then row A. Right? And so this is actually equal to row A FA tensor row B FB. Right? So the products go factor-wise. Actually, another rule here that you can check, which is also utterly trivial, is that how to do adjoints of these guys. And finally, in order to verify this, here you can see that already you can simplify this, putting the factors together. So the only thing that remains is to compute the trace of a product. Now let's do that. So trace of A tensor B. Any guess? You can guess from there. It's supposed to be the product of the traces. So let's do it. What is the trace? The trace is a sum over the diagonal elements of this operator. Now, I need a basis for this product space. I gave you a basis, which is that. Right? So this will be mu alpha. It's the sum over mu and alpha. A tensor B. Mu alpha. And if you feel more comfortable with it, think of mu alpha just as a shorthand of the tensor product of vectors. Then you find mu tensor psi alpha. So on that basis. Now, I told you how this tensor product operator acts on a product vector. Just acts factor-wise. And the scalar product also goes factor-wise. That was the basic definition of scalar product here. Right? So everything goes factor-wise. So this is equal to the sum of mu and alpha, mu A mu times alpha E alpha. And that's the product of the traces. I just put the sum there. So this is trace A times trace B. So if we define our operators like that, then everything is the statistical interpretation of independent experiment works out. But the whole thing would be totally boring if that's the only thing we can do. Right? At the end, it will be all about non-product measurements and preparations. Those are much more interesting. But we can still test them by using the separate lab scenario. Actually, one thing I didn't tell you, if I have two positive operators, A and B, is their tensor product also positive? This is actually a little bit subtle. That will be part of our description of the positive cone, next chapter. So next session actually will be tomorrow at 12, right? And I think it's in the other room. It's 268 or so. David already changed and stood IP, or tried to at least. Maybe this is done after the overnight service period. Change the rooms and the times so they are now correct. I thought it would be stupid to have stood IP pointing to Monday for the whole term. Nobody's going to be there. So tomorrow 12, should we take 12 o'clock, 12:15 or 12 sharp? Are there preferences from your side? 12:15 is good enough. There's still enough time to get it right. We had that on Monday already. Okay, so I close here. The next. So the preview of what is coming up is explaining what a channel is with a few examples of channels, what complete positivity, how the corresponding stuff looks in the classical case. And then starting with an analysis of the positive cone, which is one of the key structures that we discussed.
Well, if we have like indistinguishable particles and
that's another story. Sure. Okay, so see you.